Section 12.3, we're going to add to our repertoire of constructions how we can create different things. And we're actually going to construct parallel lines as our next objective. And there are two constructions for parallel lines. One is actually where you can create a rhombus to create the parallel lines. And then the other one is to create corresponding congruent angles. And if corresponding angles are congruent, we know lines are parallel because that was a fact that we did back in the last chapter. Do you remember that? So we're going to use two different ways to construct parallel lines. All right, so before we can do our next construction, we need a definition. Definition of angle bisector. An angle bisector is a ray that separates an angle into two congruent angles. It bisects, i.e. cuts an angle in half. Now, you can attempt, you might be even successful, at creating an angle bisector by folding along a paper. So if you had the angle on the paper, you lined up the two sides, you could fold it and you could get a fairly good estimate of where the angle bisector would be, right? So that's one way to do it. Another option for how to do that is to use your compass and your straight edge, and that's the one we're going to do for our next construction. Okay? All right, a little bit more about some angle bisector stuff. All right, so we found how to construct an angle bisector. Any point that's on the angle bisector, I'm sorry, let me read it correctly. Any point is on an angle bisector if and only if the point is equidistant from the sides of the angle. So you can see in the first picture that ray that would go from A through O would be our angle bisector, and the point O is equidistant from P and Q. So they're talking about this line and this line segment being congruent. It is equidistant. And the reason it's creating these perpendiculars is because when we talk about distance away from something, the shortest distance is the perpendicular distance. So that's what they're measuring there. Notice the distance from the point to a line is the length of the perpendicular segment from the point to the line, because the perpendicular is the shortest one. That's what I was talking about. And if you talk about, like, well, why do I always know that I'm going to get this to happen? If you take a look at the second picture, what you see is you see triangles, don't you? Yes, you do. And in those triangles, you have some things that you know are congruent. In particular, you know that you have a congruent angle right here because it's an angle bisector. That's the whole point, right? You also know that you've got these congruent pieces right here. These are the angles that are the right angles. And you know that you have this line in between here, yes? It's the same line in both triangles. So let's see, we've got an angle, we've got a line here, we've got an angle here. What is it that we actually have in terms of a triangle congruence theorem that would make these two triangles congruent? Angle, angle, side. So if you remember, any two angles and one side in a triangle are enough. And this one would be angle, angle, side. So these triangles are congruent. And since the triangles are congruent, it automatically means that these two segments are congruent. Why? CPCTC, corresponding parts. They are corresponding parts of these congruent triangles, so they're also congruent. Okay? So I'm never asking you to write out a formal, detailed proof, but I ask you, and your book asks you several times to justify, which means stating something and saying why you know it's true, right? That's what we're looking for, a justification of why it's true. And that would be the justification for why we know that P is equidistant from D and E in that last picture, or that O in this one is equidistant from P and Q in the first picture. Okay, corresponding triangles, or congruent triangles with corresponding parts. In center. So this is a fun one, and I think this is the one we get to create. I can't remember when we create it, but at some point, maybe it's next lesson. The in center. The in center is the single point of intersection of all three angle bisectors of a triangle. So all three of the angle bisectors will intersect in the same location, and that point is called the in center. And all those points are equidistant from the corresponding sides. That's what we just said in the last one right there. So the in center is actually the location that is equal distances from all three sides of this triangle. What that means is if you set your compass to have a width that goes from that in-center point P to any one of those edges, you can create a triangle in the middle of it. I didn't say that right. A circle is what I meant to say. You can create a circle in the middle of the triangle, and that's what the picture shows. The in-center creates a triangle. No, I did it again. A circle inside of a triangle. That's the one I want here. I want a circle inside of the triangle. We did a construction, I don't know if it was last time or 2 times ago, where we created a circle around a triangle. I said it right that time. The circle was around the triangle, okay? And this one creates a circle inside of the triangle. All right? We know that the 3 distances are equal. I already talked about that one, actually. And the reason why is because they are all angle bisectors. And angle bisectors are equidistant from the sides of the angles. Tangent line. A tangent line is a line that intersects a circle at exactly one point. Okay? So I've had people describe a tangent line as kissing the circle, or bouncing against the circle. It's just a one single touch and it's off. And then a line perpendicular to the radius of the circle is tangent to the circle. So when you're looking back at this picture, the line CB, the top line here, CB, it just touches the circle at point M, and when it does that, it creates a perpendicular segment there. Okay, those are corresponding statements. They go together. So all of these are tangent lines. So CA over here on the left is tangent to the circle P. The line at the bottom, AK or AB or KB, whatever you want to label it, is tangent to the circle at point K. Okay, and they all create these perpendicular segments. All right, our end circle, or more about our end circle. So the sides, this is what I was just saying, the sides in triangle ABC from the last figure are all tangent to the circle with radius PK or PM or PN. When we do that, we actually give a special name to the circle. The circle is called the inscribed circle of the triangle. Or we can say the circle is inscribed in the triangle. That makes sense. When we did the circle around the triangle, we called it circumscribed. It's encircling it. It's inscribed. It's inside of it. And the center of the in circle is the in center. They all have the word in front, just like all the other ones had the word cir, C-I-R, circumcircle, circumscribe, circum, it was in front of it. All right, there are 2 constructions on this last one, and we will wait till next time because I don't have time to do both of them, and they're both really the same construction description. So let me, before you pack everything up, give me just a minute more to describe what they're going to do. And then next time we'll do these 2 constructions, we'll move into 12.4, and we'll do group work from 12.3. Sound good? Okay. So we're going to create perpendicular lines. We started out this section with creating parallel lines, right? And there were 2 ways to create parallel lines, using the rhombus method and using the congruent angle method. We're going to create perpendicular lines in this one, and there's going to be 2 different, they aren't 2 different methods, but they're 2 different locations where the point can be located. So on your paper, it's probably even drawn in. One is a point that's actually on the line you already have and wanting to create a perpendicular line. The other one is if a point is off of the line you already have. So that would have been like the picture I had at the very beginning when I was creating my parallel lines. In fact, it's probably copied and pasted, and it's the same picture, right? Yeah. So we're going to create perpendicular lines using both points on the line and points off the line, and we'll do that next time.